Concurrent forces. The forces acting on the same point are known as concurrent forces. If the number of forces acting on the body produces zero resultant force, then these forces are said to be in equilibrium. Here is a piece of meat and three dogs are pulling this and applying force F1, F2 in this direction and F3 in this direction. The forces are concurrent because the line of action passes through the common point. Two or more concurrent forces can be balanced by a single force called equivalent force. Here we have two forces, force F1 and force F2. Force F1 is equals to 763 Newton and force F2 is equals to 525 Newton, and their resultant is 926 Newton, making an angle 34.5 degree along with x-axis. Here the equivalent force is same in magnitude. F equivalent is same in magnitude of F resultant, that is 926 Newton, but it is opposite in direction. In this case, Fe equivalent force is equals to 926 Newton at an angle 214.5 degree. We can calculate this by adding 34.5 with 180 degree. This angle, complete angle is 180 degree, and this angle is equals to this angle, that is 34.5. So by adding 34.5 and 180 degree, we get 214.5 degree. Torque or moment of force. Definition: the turning effect produced in a body about a fixed point due to an applied force is called torque or moment of force. In simple wording, when we apply a force on a body at a fixed point, so the turning effect is called torque or moment of force. Or in other wordings, the vector product of the position vector from the axis of rotation to the point of application of the force and the force vector is called as torque. Here we have a spanner and a nut. We are rotating this spanner to move this or rotate this nut about a fixed point. We apply force at this point, and the distance from this fixed point to this point at which force is applied is r, and this distance r and applied force are right angle or perpendicular to each other. Torque is cross product of position vector, this distance, and force applied on this spanner, R cross F. We know that cross product gives us function of sine, and we get torque is equals to magnitude of R and magnitude of F into sine theta into unit vector. When we represent vector, we write magnitude of vector into unit vector. Here R is perpendicular distance. This distance is perpendicular to the applied force, and F is magnitude of applied force. Unit of torque is Newton meter. Newton is unit of force and meter is unit of this distance. Torque due to force acting on a rigid body. Here we have a nut and a wrench. We are rotating this nut about a fixed point by the help of this wrench. When we apply force on this point on this wrench, the nut is rotated by the help of this wrench. The distance from this fixed point to the force applied is R. This applied force can be divided into its two components. We can split force F into Fy component, that is Fy is equals to F sin theta, and Fx component, that is equals to F cos theta. Here F cos theta is parallel to the distance R, so that is position vector, and this component of force, that is F cos theta, will not produce any rotation of this wrench because its line of action passes through the pivot point. So the rotation is done by this Fy component. So the effective component of force that produces the rotation is F sin theta. So we have torque is equals to R into F sin theta in magnitude form. When force is acting perpendicular, then it is completely effective to produce turning. So perpendicular means angle is 90 degree. By putting angle theta is equals to 90 degree, we get maximum force. Torque is equals to R into F is maximum force because sine 90 gives 1, and 1 multiplied by RF is R into F. And when we put theta is equals to 0 degree, then we get 0 torque. When R and F are parallel, so we get 0 torque. Vector representation of torque is given here. Torque is equals to R cross F, and by replacing cross we get R into F, magnitude of position vector and magnitude of force, into sine theta into unit vector. Torque or moment of force. As we discussed in previous slide, we can split this force vector into its component and its effective component, that is F sin theta perpendicular to the position vector R, can be multiplied by R to get torque. So in this condition we can take the magnitude of position vector R and magnitude of force F and multiply it by sine theta, and by writing unit vector we can also write it as torque is equals to R cross F, because sine theta shows that it is vector product. We can also write this equation by associating the sine function with the distance as R sine theta, and by multiplying it with force we can get torque. Here we have splitted R into its component. We draw a perpendicular from R on force F, and this perpendicular component of R is R sine theta. So we can multiply this R sine theta with magnitude of force to get torque. And we write here unit vector to represent the direction of vector. And sine theta is replaced by cross, so torque is cross product of force and position vector r. Here r is d, this perpendicular distance, and magnitude of torque is equals to F into d. Dependence of torque. Torque depends upon magnitude of force, perpendicular distance from axis of rotation to line of action of force called moment arm, that is position vector r, angle between applied force and position vector theta. Theta is the angle between F and R. When theta is 90 degree, we get maximum torque. When theta is 0 degree, we get minimum torque. For convention, we say that for counterclockwise rotation, torque is positive. For clockwise rotation of object or body, torque is negative. Unit. The SI unit of torque is Newton meter and its dimension is m, L to the power 2 and T to the power minus 2. Its dimensional formula of torque. Examples. Tightening of a nut with a spanner. As we saw in previous slide, we can tighten a nut by the help of a spanner, and there is torque generated due to applied force, because applied force produce the torque or rotation about a fixed point on nut. A seesaw rotates on and off the ground due to torque imbalance. Force torque analogy. Just as force determines the linear acceleration produced in a body, the torque acting on a body determines its angular acceleration. As we know that by the help of force we can determine the linear acceleration. So similarly, by the help of torque we can determine the angular acceleration produced in an object or body. Torque is the rotational analog of force. If the body is at rest or rotating with uniform angular velocity, the angular acceleration will be 0. We know that for producing acceleration, change of velocity is mandatory. Here, when angular velocity is uniform, so there is no change in angular velocity. That's why angular acceleration will be 0. In this case, the torque acting on the body will be 0. If object is rotating but its angular velocity is constant or uniform, then there is no torque applied on this object. Torque is equals to I into alpha. Here alpha is angular acceleration. If angular acceleration is 0, then torque is equals to 0, because here uniform angular velocity is produced due to uniform angular velocity. There is no change in velocity and angular acceleration is 0. So due to 0 angular acceleration, torque is also 0. Moment of a couple. It is defined as two parallel forces that have the same magnitudes but opposite directions and are separated by a distance x. Here we have force on this edge and another force on this edge. They are separated by a distance x, but they are opposite in direction, having same magnitude. So because they have same magnitude and opposite in direction, that's why we say that this case or this condition is representing moment of a couple. Equilibrium. When all the forces that act upon an object are balanced, then the object is said to be in a state of equilibrium. Here, when we have only two cars and they are in balanced condition, so we say that it is the condition of or state of equilibrium. If an object is at equilibrium, then the forces are balanced. In this condition, forces are balanced when there are only two cars because their forces are balanced and they are in equilibrium condition. Balanced is the key word that is used to describe equilibrium situations. Thus, the net force is 0 and the acceleration is 0 meter per second square. But when another car is also present here, so forces are not balanced due to another car, so equilibrium condition is disturbed. Now this is unbalanced state, so it is not condition of equilibrium. A body is in translational equilibrium if it is at rest or is moving with constant speed in a straight line. A body is in rotational equilibrium if it is rotating with constant angular speed about a fixed axis. Types of equilibrium. There are two types of equilibrium. Static equilibrium. If a body is at rest, we say that it is the condition of static equilibrium. For example, a book laying on a table, bulb hanging from a ceiling. Second type of equilibrium is dynamic equilibrium. If a body is moving with uniform velocity, for example, a paratrooper falling down with constant velocity and a car moving with uniform linear velocity. Conditions of equilibrium. There are two conditions of equilibrium. First condition of equilibrium. If the vector sum of all the forces acting on a body is equal to 0, then the body is said to be in equilibrium. For this condition, summation of forces equals to 0. Summation of forces, all the forces acting on x-axis are taken as 0. So summation of Fy is also equals to 0. That is, forces acting on y-axis is equals to 0. So this condition is known as first condition of equilibrium. Second condition of equilibrium. It states that if the vector sum of all the torques acting on a body is equal to 0, then the body is said to be in equilibrium. So for second condition of equilibrium, summation of torque, all the torques acting on a body must be equals to 0. Principle of equilibrium. Sum of clockwise moment or torque is equals to sum of anti-clockwise moment or torque. Although first condition of equilibrium is satisfied, yet it may rotate in the anti-clockwise direction. In all such cases where the forces are applicable on a body in such a way that they may cause a torque in a body, then equilibrium is checked by applying the second condition of equilibrium. Now we are in a position to state the complete requirements for a body to be in equilibrium, which are summation of forces equals to 0, such as summation of forces along x-axis is equals to 0 and summation of forces that are along y-axis must be equals to 0. Second condition of equilibrium is summation of all the torques is equals to 0 or summation of clockwise torque is equals to summation of anti-clockwise torque. For a body to be in complete equilibrium, both the conditions must be satisfied. Both linear and angular acceleration must be 0. Thank you. Take care.